In this video, we're going to talk about vectors in the plane, looking at how we can represent vectors algebraically. Consider the vector on screen. It appears to be going up and to the right. Now, of course, that's from the perspective of you as the viewer sitting and looking at the vector from this perspective. Someone else, sitting over here and facing the opposite way, sees the vector going in a different direction. They see it going down and to the left. And this really reinforces the idea that a vector is kind of meaningless without any sort of geometric reference frame to look at it through. This is why all vectors have to be built upon what's called a basis, or a set of basis vectors. They sort of make up the fundamental ingredients that all other vectors can be built on. And because we are very accustomed to representing things within the Cartesian plane, our basis vectors are going to be very much rooted within that system. The basis vectors that define our vector system are set up along the positive x and y axes. We use vectors that are called unit vectors, which means they're of length 1. So we have a basis vector along the positive x-axis of length 1. And we call that basis vector I. And then we have another basis vector along the positive y-axis. It is also length 1, and we call that vector j. Using these basis vectors, what I can do now is take any point in the Cartesian plane, like the point 4, 6, for example, and I can express a vector going from the origin to that point using my basis vectors. So this vector going from the origin to the point 4, 6 can be built by taking 4 of the unit vector I along the x-axis and adding to that 6 of the unit vector j going along the y values. This gives us one of our algebraic methods of representing vectors. We could actually represent this vector, let's call it vector OP, because it goes from the origin to a point P. We can represent it as the sum of 4 of the vector I plus 6 of the vector j. And that becomes our first algebraic notation for dealing with vectors. There's another notation we use to represent vectors algebraically. We call that form of vector representation, we call it column vectors. And this is the way it looks. We basically say, well, this is a component related to x. It tells me how far, when I'm making the vector, how far I would go left or right. And this value in front of j represents a y component for the vector. It tells me how far I have to go up or down to construct the vector. And so column vectors simplify the notation a little bit by simply taking your x component and your y component and writing them in a column, and then framing that with these larger parentheses. This is a far more common notation for vectors. This column vector notation is far more commonly used, though, in mathematical applications, whereas you tend to see this version used a lot more in physics and science-based applications. So both of them are really useful, really valid. You'll need to be able to read and interpret both, but they do kind of cater to different disciplines. So let's draw vectors using both types of notation. So a vector 4i minus j is a vector that goes 4 units to the right and a single unit down. So that vector would look something like this. If I asked you to draw the vector -2, 3, then that means I'm going 2 units to the left and 3 units up. And then this would be the resultant vector going in that direction. So you can see how this algebraic notation connects very closely to the geometric representation and just gives us another way of representing vectors. This is going to be useful, though, because a lot of operations with vectors, it's easier to do algebraically than geometrically. So algebraic notation is going to pay off in a big way. Also, fun fact, you've actually seen column vector notation before. This came up when we did transformations last year. We used this notation to represent a translation for a function, whether a function shifted left or right and up or down. It's the same ideas that we were seeing then cropping up again in another context. Go figure that all of math is so intricately connected.